Exponential equations, so how we solve them. The simplest ones, I guess, are ones like this. 5 to the power of x equals 125, where we can rewrite the number with the same base. And 125, of course, is 5 cubed, so x would be 3. This one's not as obvious, but we could rewrite both of these as base 2, because 4 is 2 squared, and on the right hand side we have 2 to the power of negative 3 on 2. Just playing around on the left hand side, that power, because we multiply the powers, becomes 4x plus 2, and eventually we get x is minus 7 on 8. But then we get ones like this. There's no way in the world I'm going to easily rewrite 32 as 7 to the power of something. And that's where our logs come in handy. So remember, logs were the inverse of exponentials. So yesterday we saw turning the log into an exponential. Now we're going back the other way. And remember, the key is the base simply stays the same. So if I want to undo that exponential, then I log both sides. So it's log 32 base 7. Well, that doesn't really help me if I want to find an actual number, because we don't have a log base 7 button on our calculator. And that's where the change of base formula comes in handy if we do want to use our calculator. Because on our calculator we only have 2 log buttons. There's the one that actually says log, that's base 10, and the one that says ln, which you might have thought was the in button, but it's actually ln, and that's natural logarithm, base e. So how do we use it? Well, we say, well, I don't have a button for log base 7, but I do have a button for log base 10, or the natural one. I haven't bothered writing the base there. So I say, well, I will find that one, but I have to divide it by the log of the original base. So in this case, log 7. As I say, it does not matter which log button you use, you just have to use the same one for both the top and the bottom of the fraction. And we'll get our answer. And we can check if we're unsure, because if we now put 7 to the power of 1.781 in our calculator, well, we're not going to get 32 exactly, because that's an approximation, but we'll get pretty close to 32. So 3 to the power of x equals 5 to the power of x minus 2. Well, which base? Well, I'll just log both sides. And let's play around with it. We have a log law that says we can bring that power to the front. I can rewrite it as x log 3 equals x minus 2 log 5, and I just got to make x the subject of this equation. But playing around with it, eventually we get x equals 2 log 5 over log 5 minus log 3. Again, it doesn't matter which log button I press. I just got to use the same one for all 3 calculations. And we get 6.301. Might not be immediately obvious, but what we've got here is a quadratic equation, because 9 is 3 squared. So I could rewrite it. If I imagine m was this new pronumeral and it was 3 to the power of x, m is 3 to the power of x, well, that means m squared actually turns out to be 9 to the power of x. You see how I got there? So m squared would be 3 to the power of x squared. Then I use my index laws, that becomes 3 to the power of 2x. But then I could go back with my index laws again and say, oh, well, that's the same as 3 squared to the power of x, which is 9 to the power of x. I really got this quadratic equation, m squared minus 4m plus 3, which does factorise nicely, 3 and 1. So there are our 2 possibilities. Well, that answers for m. We're not actually trying to find m, we're trying to find 3 to the power of x. So what we're saying is either 3 to the power of x is equal to 3, or 3 to the power of x is equal to 1. Well, 3 to the power of x is equal to 3, x must be 1. And if 3 to the power of x is equal to 1, x must be 0. There's our 2 answers for this equation. Just a little thing about inequations and continually increasing or decreasing functions. When we solve inequations, or equations for that matter, we usually say, well, what we do to one side of the equation, we'll do to the other. So we would just, with exponential equations, we say, oh, we're going to log both sides. Now you can do that with inequations as well, because what happens is if you apply a function to an equation, or actually more an inequation, if you apply a function to an inequation, the inequality sign will stay the same so long as that function is continually increasing over that interval that you're interested in. So always going up. You'll change the sign if it's continually decreasing. way of explaining that. Here's a hyperbola. Remember when we did inequalities and inequations, I said if you take the reciprocal of both sides, you change the sign? Well, this is why. Because if I look at this function and I'm trying to do an inequality between, say, let's say I'm going between 1 and 3, well, the curve is continually decreasing. So that's why we change the sign. It's the function we're applying to the inequation. So what that means is, if we get this really strange inequality to think about, we've got to work out where x is. But we know 2 to the power of x goes between 1 and 32. Well, I can apply the log function, because we know the exponential and the log function, both of them, are continually increasing. If you think of their curves, they're always going up. The log function goes like that, the exponential function goes like that. So the inequality sign will stay the same. So that means I could rewrite this as the log of 1 is less than the log of 2 to the power of x is less than the log of 32. And I'm using base 2 here, so I can play around with the middle one. Because the middle one, I could bring the power to the front, and that would give me x log 2 base 2. But we had that log rule that said log a base a is always equal to 1. So now I've just got x in the middle. The left hand side, we had a rule that said log of 1 is always equal to 0. And then on the right side, I've got log of 32 base 2. Well, 2 to the power of 5 is 32. So that would be 5. I've got my answer. X must go between 0 and 5. Same sort of idea now. If I've got the log of x is greater than 2, so this time I'm going to apply the exponential function to it. But an exponential is also continually increasing. So I can rewrite that as 3 to the power, keep the base the same, so 3 to the power of log x, base 3, is greater than 3 squared. 3 to the power of log 3, exponentials and logs cancel each other out, the bases are the same, so that'll just be x, and on the right hand side 3 squared is 9. That has the solution x is greater than 9. Okay, that shall do us. So 8E, we've got a handful of questions there to look at.